Hello, in this video we're going to do a quick little proof of the chain rule. Now this proof I'm not sure works for all functions. There's a couple of really powerful assumptions we're going to have to make. We'll get to them as we come along, but I think it's pretty much going to work for all the functions we have to deal with in high school, and that's where this video is primarily aimed. So, well, at the time of this video anyway, I don't think we're going to have to deal with anything more complicated than this. You future people, gee, I don't know. I hope you're okay. I'm sure you'll be fine. Okay, anyway, for us now in the present, let's begin. So remember, the chain rule says that if you have a function f of x and it's equal to a function of another function of x, so a function y of a function u of the variable x, then we have that f prime of x is equal to y prime of u of x, so y prime at the point u of x times u, that's a horrible times u prime of x. I'm not even going to bother to write the times in. Okay, so f prime of x is equal to y prime of u of x times u prime of x. That's what we're trying to prove. However, in order to prove that, let's go into the definition of the derivative again. We know that f prime of x, it's still equal to the limit as h tends to 0 of f of x plus h minus f of x divided by h. We know that. In other words, it's how much does f change by compared by how much x changes by. So the top is the change in f, the bottom is the change in x. Well, putting in our y of u of x definition, this is equal to the limit as h gets closer and closer to 0 of y of u of x plus h minus y of u of x divided by h. Still no difference here. Okay, oh, the only difference is we've put in the definition of f of x plus h and the definition of f of x, but that's all fine. Okay, but now we want to do something a little tricky. So this is equal to the limit as h tends to 0. Well, we're not concerned with when h does equal to 0. We're only concerned with what happens as we get closer and closer to 0. And since we're trying to show that the derivative of this thing is equal to the derivative of y times the derivative of u, we really should have like a change in u on the bottom and then a change in u on top if we're going to really work things out. So that's what we're going to do. With the goal of showing that that's true, we're going to divide by the change in u and then times by the change in u. So that's what we're going to do here. So this is equal to the limit as h gets closer and closer to 0 of y of u of x plus h minus y of u of x divided by u of x plus h minus u of x, and then times u of x plus h minus u of x divided by h. And the reason we've done this is because, well, first of all, this thing looks suspiciously similar to u prime of x, to that part of the u prime of x calculation, and in fact it's exactly the same as that if we're taking the limit as h tends to 0. Now this part here, we want to show that that is equal to y prime of u of x. And that's what we're going to do. Okay, one thing to note. This thing here, since we're dividing by it and timesing by it again, but in particular, since we're dividing by it, there must be some interval of the point u of x on which this thing is nowhere 0. Because we're taking the limit as h gets closer and closer to 0. We can't forever keep ignoring points where the bottom part is equal to 0. So there needs to be some interval. So there needs to be like some interval that looks something like this, where if I can draw a circle around that point u of x, there is nowhere where that difference is equal to 0. We need to have that situation. If we have a situation like this, where This is u of x. And we keep coming closer and closer, and it keeps forever giving us values that are where the difference is equal to 0. That's a problem. It can't work. So we have to assume that, whoops, rub too much out. We have to assume that given our function u, eventually we can sort of get a circle around it where there's always going to be a difference. So keep that in mind. That's one of the big assumptions we need to make before we can do this. Okay, let's get to the next part now. I've rambled on for enough. Okay, so here's where we're at. Let me rewrite it just for fun, in green this time. Limit as h gets closer and closer to 0 of y of u of x plus h minus y of u of x divided by u of x plus h minus u of x, which we're assuming is nowhere 0, times u of x plus h minus u of x divided by h. Okay, well, here's another thing. So we're going to let s equals u of x plus h minus u of x. So that's the first thing we're going to do. We're just going to call that thing s. And we're going to assume, so the second big assumption that we're going to make, as h gets closer and closer to 0, s gets closer and closer to 0. So in other words, as h gets closer and closer to 0, this function u of x plus h gets closer and closer to u of x. The value u of x plus h gets closer and closer to u of x as h gets closer and closer to 0. So that means s gets closer and closer to 0 as h gets closer and closer to 0. So that's the second big assumption that we're going to make. Okay, well, assuming those assumptions are made, if we're taking the limit as h gets closer and closer to 0 of all this stuff in green, well, it's the limit as h gets closer and closer to 0 of this thing times this thing. If they're both going somewhere as h gets closer and closer to 0, then the limit of the product will be equal to the product of the limit. Now, what I mean by that is if as h gets closer and closer to 0, this thing is going somewhere and this thing is going somewhere, then whatever this big limit is, it's going to be equal to the limit, it's going to be equal to wherever this thing goes as h gets closer and closer to 0 times wherever this thing goes as h gets closer and closer to 0. Have a think about why that's true. You can formally prove it and blah, 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 but I mean, just picturing it in your mind will do for now. We don't need to formally prove it at high school. So here's where we're at now. We're actually equal to the limit as h tends to 0 of this first thing times the limit as h tends to 0 of the second thing. Now I'm going to include this s detail. So the limit as h tends to 0 of y of u of x plus h. Well, if s is equal to u of x plus h minus u of x, then u of x plus h is going to be equal to s plus u of x, or u of x plus s. U of x plus s minus y of u of x divided by, well, u of x plus h minus u of x, that's just equal to s. And we're going to be multiplying this by the limit as h tends to 0 of this thing here, u of x plus h minus u of x divided by h. We're going to be multiplying by that. Well, finally, we're going to use our last assumption. As h gets closer and closer to 0, this s gets closer and closer to 0. So actually, I don't even need to write h here. I can just write s, because as h gets closer and closer to 0, s is getting closer and closer to 0. And so this first part, I'm going to use a different color, this first part here is actually simply y prime of u of x. Y prime of u of x, because it's equal to the limit as s tends to 0 of y of u of x plus s minus y of u of x divided by s. It's exactly what we're used to doing, except our h is now an s. And that's not a big deal, is it? That doesn't change anything. It's just a label. Okay, and similarly, this second circle is actually u prime of x by definition, because it's u of x plus h minus u of x divided by h, and we're taking the limit as h gets closer and closer to 0. So times u prime of x. And so what we started out calculating was f prime of x. We started out calculating f prime of x, and we showed that in fact it must be equal to y prime of u of x times u prime of x, given our assumptions about this thing never being 0 on some small enough interval of u of x, and and also that as h goes to 0, this thing gets closer and closer to 0. Those are the two really important assumptions. And all the functions we meet in high school, for now, will probably fit that assumption. We'll make a big deal of it when it doesn't, don't worry. Okay, thanks very much for watching. Hope that was useful. Don't forget to check out the notes that go with the chain rule. I wrote some notes that go with it, so have a look at those and do the exercises at the back. I'll do one more video where I do some examples of differentiating using the chain rule. But the theory of it is done for now. Thanks very much for watching. Take care. Bye.